Right now, the gold in your jewelry, the silver in your electronics, and the uranium in nuclear reactors all share a violent cosmic origin. They were forged in the final explosive moments of dying stars, whose deaths released more energy in seconds than our sun will produce in its entire lifetime. We thought stellar fusion could create all elements. We were completely wrong. For decades, scientists believed that the nuclear furnaces burning inside stars could forge every element in the periodic table through gradual fusion processes. But iron-56 represents an insurmountable barrier, a nuclear stability peak where fusion reactions stop producing energy and instead require it. Beyond iron, the universe needed a different mechanism, something far more violent and energetic than ordinary stellar burning. To understand the magnitude of this cosmic alchemy, consider that every atom of gold contains 79 protons, requiring nuclear processes so extreme they can only occur during the most catastrophic events in the universe. The energy needed to forge elements heavier than iron exceeds anything available in normal stellar cores, demanding temperatures exceeding 100 billion Kelvin and neutron densities approaching those found in atomic nuclei. Tonight, we're going to explore the cosmic factories that create the universe's heaviest elements. You'll discover why stellar death becomes stellar creation, how exploding stars generate conditions more extreme than anything found in ordinary stellar cores, and why the elements that make modern technology possible could only be forged in cosmic violence. But here is what makes this truly mind-bending. Supernovas don't just create heavy elements. They blast them across space at velocities exceeding 10 kilometers per second, seeding future generations of stars and planets with the chemical complexity necessary for rocky worlds and biological evolution. Every heavy element on Earth is immigrant matter from stellar explosions that occurred billions of years ago. Dr. Stan Woosley from UC Santa Cruz, whose computer simulations revealed supernova nucleosynthesis mechanisms, explains that supernovas represent the universe's ultimate nuclear reactors, operating under conditions so extreme they can forge elements impossible to create through any other natural process. These stellar explosions literally manufacture the periodic table's heaviest entries. The numbers alone are staggering. A typical core collapse supernova releases 1044 joules of energy in its explosion, roughly 100 times more energy than our sun will produce over its entire 10 billion year lifetime, concentrated into a few seconds of cosmic violence. This enormous energy drives nuclear reactions that can build elements containing more than 200 neutrons and 90 protons. What makes this revelation particularly fascinating is the realization that technological civilization depends entirely on elements that can only be created through stellar death. The rare earth metals in your smartphone, the platinum in catalytic converters, and the gold in computer circuits all require the extreme neutron fluxes and temperatures achievable only during supernova explosions. NASA's observations of supernova remnants reveal expanding shells of gas enriched with freshly synthesized heavy elements. The Cassiopeia, a supernova remnant created by a stellar explosion 340 years ago, shows clear spectroscopic evidence for newly created iron, nickel, cobalt, and elements extending well beyond the iron peak. Dr. Robert Kirshner from Harvard University, whose supernova observations contributed to the discovery of dark energy, notes that supernovas serve as cosmic element factories and distributors, not only creating heavy elements but launching them into space where they become incorporated into molecular clouds that form the next generation of stars and planetary systems. The process requires understanding nuclear physics under the most extreme conditions imaginable. During a supernova explosion, the stellar core reaches densities exceeding 1,015 kilograms per cubic meter, comparable to the density of atomic nuclei, while temperatures soar beyond a Kelvin. These conditions enable rapid neutron capture processes that can build the heaviest elements in seconds. As you sit reading this, you are surrounded by and composed of elements forged in stellar explosions. The calcium in your bones, the iron in your blood, and trace amounts of gold and silver in your body all originated in supernova explosions that scattered these elements across the galaxy billions of years ago. The story of heavy element creation is ultimately a story about cosmic recycling, how stars process hydrogen and helium into increasingly complex elements, culminating in explosive events that distribute this chemical wealth throughout the universe. Without supernovas, the cosmos would remain forever dominated by hydrogen and helium, incapable of forming rocky planets or supporting chemical complexity. If you're fascinated by the cosmic origins of matter, subscribe and the thumbs up button. And here is a question that will change how you view the world around you. If every element heavier than iron requires supernova conditions to form, what does that tell us about how rare and precious the chemical complexity of our planet really is? Comment below with your thoughts. I'll pin the most insightful response. Throughout this exploration, we'll discover exactly how dying stars become cosmic element factories, why iron represents an absolute barrier to normal fusion, and how the most violent events in the universe create the chemical diversity that makes planets, technology, and life itself possible. We'll examine the cutting-edge computer simulations that model supernova nucleosynthesis, explore the observational evidence from stellar spectroscopy and meteorite analysis, and understand how these cosmic explosions have shaped the chemical evolution of galaxies throughout cosmic history. The journey will take us from the quantum mechanics governing neutron capture reactions to the galactic-scale distribution of heavy elements, revealing how supernovas serve as both cosmic destroyers and cosmic creators, ending stellar lives while enabling the chemical complexity that makes new forms of matter and energy possible. Now let's begin our exploration of cosmic alchemy, where stellar death becomes the ultimate creative force, transforming simple atomic nuclei into the complex elements that form the foundation of technological civilization. Chapter 1. Stellar factory stars begin their lives as cosmic fusion reactors, converting the universe's primordial hydrogen into increasingly complex elements through nuclear burning processes that operate over millions to billions of years. These stellar factories represent the universe's primary mechanism for element creation, but their productive capacity faces fundamental limitations that determine which elements can be forged through ordinary stellar evolution. The stellar nucleosynthesis process begins with hydrogen fusion in stellar cores, where temperatures exceed 15 million Kelvin and pressures reach 100 billion times Earth's atmospheric pressure. Under these extreme conditions, hydrogen nuclei overcome electromagnetic repulsion through quantum tunneling effects, fusing into helium while releasing the energy that powers stellar luminosity. Dr. Hans Bethe's Nobel Prize-winning work on stellar nucleosynthesis revealed how stars create elements through a series of nuclear burning stages. The proton-proton chain converts 4 hydrogen nuclei into 1 helium nucleus, releasing 26.7 million electron volts of energy and powering stars like our Sun throughout their main sequence lifetimes. As stars exhaust their hydrogen fuel, gravitational contraction raises core temperatures to levels where helium fusion becomes possible. The triple alpha process combines 3 helium-4 nuclei to create carbon-12, requiring temperatures exceeding 100 million Kelvin due to the lack of stable mass 5 or mass 8 nuclei that would enable simpler helium fusion pathways. The stellar mass determines how far up the periodic table nuclear burning can proceed. Stars with masses less than 8 times our Sun cannot achieve the core temperatures necessary for carbon burning, ending their lives as white dwarf stars composed primarily of carbon and oxygen. These lower mass stars contribute primarily helium and carbon to galactic chemical evolution. More massive stars continue nuclear burning through successively heavier elements. Carbon burning at 600 million Kelvin creates neon, sodium, and magnesium. Neon, burning at 1.2 billion Kelvin, produces oxygen and magnesium. Oxygen burning at 1.5 billion Kelvin generates silicon, sulfur, and other intermediate mass elements. Dr. William Fowler from Caltech, whose work on stellar nucleosynthesis earned him a Nobel Prize, described massive stars as cosmic onions with shells of different nuclear burning processes operating simultaneously. The core burns the heaviest fuel available, while outer shells continue burning lighter elements through the successive stages of stellar evolution. Silicon burning represents the final stage of stellar nucleosynthesis that can produce energy. At temperatures exceeding 2.7 billion Kelvin, silicon-28 undergoes alpha capture reactions and photodisintegration processes that build elements in the iron peak, primarily iron-56, nickel-56, and cobalt-59. The iron peak represents a fundamental barrier in stellar nucleosynthesis because iron-56 possesses the highest binding energy per nucleon of any atomic nucleus. Nuclear reactions that build elements lighter than iron release energy, while reactions that build elements heavier than iron require energy input. This means normal stellar burning cannot proceed beyond the iron group elements. The nuclear physics underlying this limitation involves the strong nuclear force and electromagnetic repulsion competing to determine nuclear stability. For light nuclei, the strong force dominates, enabling fusion reactions that increase binding energy. For heavy nuclei, electromagnetic repulsion between protons becomes increasingly important, eventually requiring energy input to add more nucleons. The stellar structure during advanced burning phases reveals the complexity of massive star evolution. A 25 solar mass star near the end of its life consists of concentric shells, a silicon-burning core producing iron peak elements, surrounded by shells burning oxygen, neon, carbon, helium, and hydrogen in decreasing temperature zones extending to the stellar surface. The timescales for different burning phases decrease dramatically as stellar evolution progresses. Hydrogen burning lasts millions of years. Helium burning lasts hundreds of thousands of years. But silicon burning consumes available fuel in just days. This acceleration occurs because heavier element fusion requires higher temperatures and produces less energy per unit mass. Dr. Ken Nomoto from the University of Tokyo, whose stellar evolution calculations address massive star nucleosynthesis, explains that the iron core grows through silicon burning until it reaches the Chandrasekhar mass limit of approximately 1.4 solar masses. At this point, electron degeneracy pressure can no longer support the core against gravitational collapse. The S process, slow neutron capture, operating in certain stellar environments, can produce some elements heavier than iron, but only under specific conditions. Asymptotic giant branch stars develop neutron fluxes through reactions like carbon-13, alpha, neutron, oxygen-16, enabling slow neutron capture that can build elements up to lead and bismuth. However, this process nucleosynthesis faces limitations that prevent it from creating the heaviest elements. The slow neutron capture rates allow beta decay to compete with neutron capture, restricting the neutron-to-proton ratios achievable in such process products. Elements beyond the lid region require neutron capture rates that exceed beta decay rates. The observational evidence for stellar element production comes from spectroscopic analysis of stellar atmospheres and circumstellar material. Stars in different evolutionary phases show abundance patterns reflecting their internal nucleosynthesis history, with more evolved stars displaying enhanced concentrations of carbon, oxygen, and heavier elements. The Hubble Space Telescope's observations of planetary nebulae reveal the products of stellar nucleosynthesis dispersed into space. These expanding shells of ionized gas show enhanced abundances of carbon, nitrogen, and oxygen relative to primordial hydrogen and helium, demonstrating how lower mass stars contribute to galactic chemical evolution. Red supergiant stars like Betelgeuse exhibit atmospheric compositions reflecting advanced nuclear burning. Spectroscopic observations reveal enhanced abundances of oxygen, neon, and magnesium produced through earlier burning phases. While the stellar surface shows evidence for ongoing mixing processes that transport nucleosynthesis products from interior burning shells. The stellar wind mass loss from evolved massive stars distributes nucleosynthesis products into the interstellar medium before stellar death. Wolf-Rayet stars, representing the final phase of massive star evolution. EXHIBIT surface compositions dominated by the products of helium, carbon, and oxygen burning, indicating extensive mass loss that exposes nuclear burning products. The metallicity gradients observed in spiral galaxies reflect the cumulative effects of stellar nucleosynthesis over cosmic time. Intergalactic regions show enhanced heavy element abundances due to higher star formation rates and more efficient retention of stellar ejecta, while outer regions remain more primitive in composition. The stellar initial mass function determines which stars contribute most significantly to galactic chemical evolution. While the most massive stars produce the largest amounts of heavy elements per star, their rarity means that intermediate mass stars dominate the overall production of carbon, nitrogen, and oxygen over galactic timescales. The stellar evolution models predict that even the most massive stars cannot create elements significantly heavier than iron through equilibrium burning processes. The nuclear binding energy curve reaches its maximum at iron 56, creating an insurmountable barrier that prevents normal stellar fusion from building heavier elements. The neutron-deficient isotopes produced by stellar nucleosynthesis represent only a subset of the heavy elements observed in nature. Many stable heavy isotopes, particularly those with high neutron-to-proton ratios, cannot be created through charged particle reactions operating in stellar cores and require alternative production mechanisms. The stellar factories thus provide the foundation for cosmic element creation while revealing their fundamental limitations. Stars can transform primordial hydrogen and helium into elements up to iron through nuclear burning, but the creation of elements heavier than iron requires conditions more extreme than those found in even the most massive stellar cores. As stellar evolution approaches its violent conclusion, these cosmic factories face a fundamental crisis: the cessation of energy-producing nuclear reactions in their cores. This crisis triggers gravitational collapse so catastrophic it creates conditions where the universe's heaviest elements can finally be forged through processes impossible during normal stellar burning. Chapter 2. Nuclear Limits. The iron peak represents an absolute boundary in nuclear physics where the fundamental forces governing atomic nuclei create an insurmountable barrier to further element creation through normal fusion processes. This nuclear roadblock emerges from the competing influences of the strong nuclear force and electromagnetic repulsion, determining which elements can exist and how they can be created. The binding energy curve reveals why iron 56 occupies a unique position in nuclear physics. Nuclear binding energy per nucleon reaches its maximum value of 8.8 million electron volts at iron 56, meaning this isotope represents the most tightly bound configuration of protons and neutrons achievable in atomic nuclei. Dr. Maria Goeppert-Mayer, whose nuclear shell model earned her a Nobel Prize, explained that iron 56 represents the optimal balance between nuclear attraction and electromagnetic repulsion. Adding or removing nucleons from iron 56 requires energy input rather than releasing energy, creating a nuclear valley from which escape demands external energy sources. For elements lighter than iron, nuclear fusion releases energy because the products have higher binding energy per nucleon than the reactants. The fusion of hydrogen into helium releases 7.1 million electron volts per nucleon, while helium fusion into carbon releases 7.3 million electron volts per nucleon. This energy release drives stellar burning and powers main sequence stars. Beyond iron, nuclear binding energy per nucleon begins decreasing with increasing mass number. Creating elements heavier than iron requires energy input rather than producing energy, explaining why normal stellar fusion cannot proceed beyond the iron group elements through equilibrium burning processes. The nuclear physics underlying this limitation involves the competition between nuclear attraction and electromagnetic repulsion. The strong nuclear force operates over very short ranges, roughly 1 femtometer, and binds protons and neutrons into stable nuclei. However, electromagnetic repulsion between protons operates over longer ranges and grows stronger as nuclear charge increases. The Coulomb barrier represents the electromagnetic potential energy that must be overcome for nuclear reactions to occur. This barrier height increases with the square of the nuclear charge, making reactions involving heavy nuclei increasingly difficult. For iron group nuclei, Coulomb barriers exceed 50 million electron volts, requiring extreme conditions for nuclear reactions. Dr. Eugene Wigner's work on nuclear symmetry revealed additional constraints on nuclear stability. The nuclear shell structure creates magic numbers, where nuclei with specific proton or neutron numbers exhibit enhanced stability. Iron-56 benefits from approaching the magic number 28 for both protons and neutrons, contributing to its exceptional stability. The nuclear reaction rates governing heavy element production depend exponentially on temperature through the gamma factor, which describes quantum tunneling through Coulomb barriers. The reaction rate formula includes terms like exp 2 pi eta, where eta represents the Sommerfeld parameter that incorporates Coulomb barrier effects. Even at the extreme temperatures achieved in massive stellar cores, exceeding 3 billion Kelvin during silicon burning, the nuclear reaction rates for building elements significantly heavier than iron become vanishingly small. The exponential temperature dependence means that even modest increases in nuclear charge create enormous decreases in reaction probability. The nuclear statistical equilibrium that develops during silicon burning demonstrates these limitations clearly. At temperatures around 3.5 billion Kelvin, nuclear reaction rates become fast enough to maintain equilibrium between formation and destruction of different isotopes, creating abundance patterns determined by nuclear binding energies and statistical mechanics. Dr. David Botinsky's analysis of nuclear equilibrium revealed that iron group elements dominate the equilibrium composition because they possess the highest binding energies. Attempts to build significantly heavier elements through charged particle reactions face exponentially decreasing formation rates and increasing destruction rates. The alpha capture reactions that might build elements heavier than iron encounter increasingly prohibitive Coulomb barriers. Adding an alpha particle, helium-4, to iron-56 requires overcoming a Coulomb barrier exceeding 60 million electron volts, demanding temperatures and particle energies beyond those available in stellar cores. The neutron capture alternative faces different limitations during normal stellar burning. The S process, slow neutron capture, can produce some elements heavier than iron when neutron sources like carbon-13, alpha, neutron, oxygen-16 operate in stellar environments. However, S process rates are limited by the competition between neutron capture and beta decay, restricting the neutron-rich isotopes that can be created. The nuclear flow patterns during S process nucleosynthesis follow the valley of beta stability, where neutron capture and beta decay rates balance. This pathway can reach elements as heavy as lead and bismuth, but cannot penetrate to the neutron-rich isotopes required for creating the heaviest stable elements. The nuclear waiting points in S-process nucleosynthesis occur at isotopes with very small neutron capture cross-sections or very long beta decay half-lives. These bottlenecks prevent rapid neutron capture and limit the endpoint isotopes achievable through slow neutron capture processes. Dr. Franz Kapler's experimental work on neutron capture cross-sections revealed the nuclear physics governing S-process pathways. Isotopes with magic neutron numbers exhibit particularly small neutron capture cross-sections, creating traffic jams in the S-process flow that determine abundance patterns. The R process, rapid neutron capture, requires neutron densities exceeding YY neutrons per cubic centimeter, conditions unavailable in normal stellar environments. These extreme neutron fluxes would enable neutron capture rates that greatly exceed beta decay rates, allowing the creation of extremely neutron-rich isotopes. The nuclear mass models predict that R-process nucleosynthesis could create isotopes with neutron-to-proton ratios approaching the neutron drip line, where neutrons become unbound. These exotic isotopes would subsequently undergo beta decay chains to produce the stable heavy elements observed in nature. The nuclear fission barriers become important for the heaviest elements created through neutron capture processes. Isotopes heavier than mass number 260 face spontaneous fission lifetimes that become vanishingly short, effectively terminating nucleosynthesis processes and defining the upper limit of element creation. The superheavy element research conducted at facilities like GSI and Riken demonstrates these nuclear limits experimentally. Elements beyond lawrencium, atomic number 103, exhibit increasingly short half-lives due to spontaneous fission, confirming theoretical predictions about the limits of nuclear stability. The island of stability predicted around atomic number 114 and neutron number 184 might extend the range of possible elements slightly, but even these superheavy nuclei would have half-lives measured in seconds to minutes rather than geological timescales required for astronomical significance. The exotic nuclear processes like pigment-nuclear fusion, which might occur in extremely dense environments, face fundamental limitations from nuclear shell effects and Pauli exclusion principle constraints. Even under white dwarf or neutron star conditions, these processes cannot efficiently produce elements significantly heavier than iron. The nuclear photodisintegration processes that become important at high temperatures also limit heavy element production. At temperatures exceeding 3 billion Kelvin, high-energy photons can break apart heavy nuclei faster than nuclear reactions can build them, creating an effective ceiling for nuclear mass in thermal environments. The nuclear reaction networks governing stellar nucleosynthesis include thousands of isotopes and hundreds of thousands of nuclear reactions, but the fundamental physics limits embedded in nuclear binding energies constrain which pathways can produce significant amounts of heavy elements. The computational stellar evolution models that follow nuclear burning through all evolutionary phases confirm that massive stars can create substantial amounts of elements up to iron and nickel, but production of elements significantly heavier than the iron peak requires conditions beyond normal stellar nucleosynthesis. These nuclear limits explain why stellar evolution alone cannot account for the FIDUS, observed abundances of elements heavier than iron in the universe. The creation of gold, platinum, uranium, and other heavy elements demands conditions more extreme than those found in stellar cores, conditions that become available only during the most catastrophic events in stellar evolution. Chapter 3. Explosive death. When massive stars exhaust their nuclear fuel and can no longer support themselves against gravitational collapse, they die in explosions so violent they create conditions more extreme than anything found during normal stellar evolution. These supernova explosions represent the universe's ultimate nuclear reactors, generating temperatures, densities, and neutron fluxes capable of forging elements impossible to create through any other natural process. The core collapse process begins when a massive star, S-iron core, reaches the Chandrasekhar limit of approximately 1.4 solar masses. At this critical point, electron degeneracy pressure can no longer support the core against its own gravity, triggering catastrophic collapse that compresses stellar matter to nuclear densities in less than 1 second. Dr. Subramanian Chandrasekhar's groundbreaking work revealed that stellar cores face an inevitable crisis when nuclear burning ceases. He described the collapse as gravity's ultimate victory over all other forces, creating conditions where matter behaves according to physics normally confined to atomic nuclei, but operating on stellar scales. The collapse velocity reaches 30,000 kilometers per second, roughly 10% the speed of light, as the stellar core contracts from Earth's radius to just 20 kilometers diameter. This represents one of the most rapid and dramatic transformations in the universe, concentrating a solar mass worth of matter into a sphere smaller than Manhattan. During collapse, the gravitational binding energy release exceeds joules, roughly 100 times the total energy our Sun will produce throughout its entire 10 billion year lifetime, concentrated into seconds. This enormous energy drives the explosion that blasts the star apart while creating conditions for heavy element nucleosynthesis. The core reaches densities exceeding 5 kilograms per cubic meter, approaching the density of atomic nuclei. At these densities, normal atomic structure breaks down. Electrons are forced to combine with protons to form neutrons, and matter exists in a state found nowhere else in the universe except neutron star cores. Dr. Hans Bethe, Nobel Prize-winning analysis of supernova mechanics revealed how core bounce creates the shock wave that powers the explosion. When the collapsing core reaches nuclear density, it suddenly stiffens, causing infalling material to rebound and launch a shock wave outward through the stellar envelope. The shock wave initially stalls several hundred kilometers from the core as it encounters the enormous amount of infalling material. However, energy deposition from neutrinos streaming out of the collapsed core can revive the shock, enabling it to propagate through the entire stellar envelope and blast the star apart. The explosion energy typically ranges from YY to YY joules, launching stellar material into space at velocities exceeding 10,000 kilometers per second. This velocity is sufficient to overcome the star's gravitational binding energy and disperse nucleosynthesis products throughout the surrounding interstellar medium. The temperature profiles during the explosion create multiple zones where different nuclear processes operate. The innermost regions reach temperatures exceeding 10 billion Kelvin, while outer zones experience temperatures from 1 to 5 billion Kelvin, enabling different nucleosynthesis mechanisms to operate simultaneously. The neutron flux generated during core collapse represents the most extreme neutron environment available in nature. Neutron densities can exceed yn neutrons per cubic centimeter, conditions that enable rapid neutron capture rates far exceeding anything possible during normal stellar evolution. Dr. Stan Woosley's computer simulations of core collapse supernovas reveal the complex hydrodynamics governing the explosion. The simulation shows how the shock wave propagates through stellar material, heating it to billions of degrees while creating the extreme neutron fluxes necessary for process nucleosynthesis. The alpha-rich freeze-out process occurs in the innermost explosion zones where temperatures exceed 5 billion Kelvin. Under these conditions, nuclear statistical equilibrium initially favors complete dissociation into protons, neutrons, and alpha particles, which then reassemble into heavy elements as the material cools. The explosion creates multiple mass elements simultaneously through different nuclear processes. Alpha-rich freeze-out produces isotopes near the iron peak, while explosive oxygen and silicon burning create intermediate mass elements, and neutron capture processes build the heaviest elements. The shock-heated material undergoes explosive nuclear burning on timescales of seconds, rather than the millions of years typical for stellar core burning. These rapid nuclear processes can significantly alter the abundance patterns produced compared to equilibrium stellar nucleosynthesis. The neutron excess in shock-heated material enables nuclear flows that are impossible during normal stellar burning. The high neutron-to-proton ratios allow nuclear reaction, networks to access neutron-rich isotopes that serve as stepping stones to heavy element production. Dr. Michael Wiescher from the University of Notre Dame, whose experimental nuclear astrophysics work addresses explosive nucleosynthesis, explains that supernova explosions create nuclear reaction conditions that cannot be replicated in any terrestrial laboratory. The combination of extreme temperature, density, and neutron flux enables nuclear processes that operate nowhere else in the universe. The R process. Nucleosynthesis requires neutron densities exceeding 1,020 neutrons per cubic centimeter and temperatures around 1 billion Kelvin. These conditions may be achieved in the neutrino-heated ejecta or a material processed through the collision between the explosion shock and the stellar envelope. The nuclear reaction timescales during R-process nucleosynthesis become comparable to or faster than beta decay timescales. This allows neutron capture to proceed along paths far from the valley of beta stability, creating extremely neutron-rich isotopes that subsequently decay to produce stable, heavy elements. The explosion asymmetries revealed by modern supernova observations suggest that core collapse events are inherently three-dimensional phenomena with complex mixing and instability patterns. These asymmetries affect nucleosynthesis by creating regions with different temperature, density, and neutron flux profiles. The Type A supernovas, resulting from white dwarf explosions rather than core collapse, produce different abundance patterns dominated by ion peak elements created through explosive carbon and oxygen burning. These thermonuclear explosions contribute primarily to galactic iron enrichment rather than heavy element production. The hypernovae or collapsor events, representing the most energetic core collapse explosions, may create even more extreme conditions for heavy element nucleosynthesis. These events, often associated with gamma-ray burst production, can achieve explosion energies exceeding 1,045 joules. The neutron star mergers represent an alternative site for process nucleosynthesis that has gained attention since the detection of gravitational waves from colliding neutron stars. These events create neutron-rich material ejected at high velocities, providing another mechanism for heavy element production. The observational evidence for explosive nucleosynthesis comes from spectroscopic analysis of supernova light curves and remnants. The radioactive decay of nickel-56 to cobalt-56 to iron-56 powers the optical light curves of Type A supernovas, while core collapse events show evidence for multiple radioactive isotopes. The supernova remnant observations reveal expanding shells of material enriched with freshly synthesized elements. The Cassiopeia A remnant shows clear evidence for explosive nucleosynthesis products, including enhanced abundances of titanium, chromium, manganese, iron, and nickel. The stellar explosion models must account for the complex three-dimensional structure of massive stars at the time of core collapse. The presence of convective zones, composition gradients, and rotation effects all influence the explosion dynamics and nucleosynthesis outcomes. The magnetic field effects during core collapse may create additional asymmetries that affect heavy element production. Magnetorotational explosions could generate the strong magnetic fields observed in magnetars, while creating unique conditions for nucleosynthesis. The exotic nuclear processes possible during supernova explosions include reactions involving unstable isotopes with half-lives much shorter than stellar evolution timescales. These processes can access nuclear reaction pathways unavailable during normal stellar burning. The element production yields from individual supernova explosions depend on the progenitor star's mass, metallicity, and rotation rate. More massive progenitors tend to produce larger amounts of heavy elements, while metallicity affects the explosion dynamics and nucleosynthesis efficiency. The supernova feedback effects on galactic chemical evolution include both element injection and energy input that affects subsequent star formation. The explosion energy can drive galactic winds that either enhance mixing or remove heavy elements from star-forming regions. These explosive stellar deaths transform dying stars into cosmic element factories operating under conditions so extreme. They approach the fundamental limits of nuclear physics while creating the chemical diversity that enables rocky planets, technological civilization, and biological complexity throughout the universe. Chapter 4. Neutron Capture. The creation of elements heavier than iron requires neutron capture processes that can overcome nuclear barriers preventing charged particle reactions from building heavy nuclei. These neutron capture mechanisms represent the universe's primary pathways for creating the heaviest elements, operating through fundamentally different nuclear physics than the fusion processes that build lighter elements. Neutron capture reactions proceed without Coulomb barriers because neutrons carry no electric charge and therefore experience no electromagnetic repulsion from atomic nuclei. This enables neutrons to approach and react with heavy nuclei even at relatively low energies, making neutron capture the dominant mechanism for building elements beyond iron. Dr. Cameron from the California Institute of Technology, whose work established the theoretical framework for neutron capture nucleosynthesis, explained that neutrons represent nature's solution to the Coulomb barrier problem. While charged particles face exponentially increasing barriers with nuclear charge, neutrons can react with any nucleus they encounter, limited only by nuclear cross-sections and neutron availability. The neutron capture cross-section determines the probability that a neutron will be absorbed by a specific nucleus. These cross-sections vary dramatically between isotopes, ranging from less than 1 millibarn for some magic number nuclei to over 1,000 barns for certain isotopes with unpaired neutrons. The nuclear shell effects create systematic patterns in neutron capture, cross-sections that influence nucleosynthesis pathways. Nuclei with closed neutron shells exhibit particularly small capture cross-sections, creating bottlenecks in neutron capture flows that determine abundance patterns in heavy element production. The beta decay process competes with neutron capture in determining nucleosynthesis pathways. After neutron capture increases the neutron number, unstable isotopes undergo beta decay with characteristic half-lives ranging from milliseconds to millions of years, converting neutrons into protons and moving nucleosynthesis toward more stable configurations. The S process, slow neutron capture, operates in stellar environments where neutron densities remain relatively low, typically 106 to Ya neutrons per cubic centimeter. Under these conditions, neutron capture rates are slower than or comparable to beta decay rates, allowing nucleosynthesis to follow the valley of beta stability. The neutron sources for S-process nucleosynthesis include reactions like carbon-13, alpha, neutron oxygen-16 and neon-22 alpha, neutron magnesium-25. These reactions occur in stellar environments where alpha particles from helium burning encounter specific isotopes to produce neutrons at rates sufficient for S-process nucleosynthesis. Dr. Franz Kapler's experimental measurements of neutron capture cross-sections revealed the nuclear physics governing S-process pathways. His work at the Karlsruhe Institute of Technology provided precise cross-section data for hundreds of isotopes, enabling detailed modeling of S-process nucleosynthesis in stellar environments. The S-process pathway follows a zigzag pattern through the chart of nuclides, with neutron capture increasing mass number by 1 and beta decay increasing atomic number by 1. This pathway can build elements up to lead and bismuth, but faces termination when it encounters isotopes that undergo alpha decay or fission. The neutron magic numbers at 50, 82, and 126 create significant bottlenecks in C-process nucleosynthesis. Isotopes with these neutron numbers exhibit particularly small neutron capture cross-sections, causing material to accumulate at these waiting points and creating characteristic abundance peaks. The branchings in SIF process nucleosynthesis occur when neutron capture and beta decay rates become comparable. Under these conditions, neutron capture can compete with beta decay, allowing some material to flow along alternative pathways that access different isotopes and final products. The stellar environment determines Psi process efficiency through temperature, neutron flux, and exposure time. Higher temperatures increase neutron capture rates through the Maxwell-Boltzmann distribution, while longer exposure times allow more neutron captures per seed nucleus before stellar evolution terminates the process. The main process component operates in asymptotic giant branch stars with masses between 1 to 3 solar masses. These stars develop neutron sources through the carbon-13 alpha neutron-oxygen-16 reaction operating in helium-burning shells, creating the neutron fluxes necessary for S-process nucleosynthesis. The weak S-process component occurs in massive stars during helium and carbon burning phases. The neon-22 alpha neutron magnesium-25 reaction provides neutrons at lower flux levels, contributing to light process elements like strontium, yttrium, and zirconium. Dr. Roberto de Lino's stellar evolution models revealed how convective mixing in a GB stars activates S-process nucleosynthesis. The third dredge-up events bring carbon-13 from interior regions to zones where alpha particles are available, triggering neutron production and S-process element synthesis. The R process, rapid neutron capture, requires extreme neutron densities exceeding YY neutrons per cubic centimeter, conditions that enable neutron capture rates much faster than beta decay rates. This allows nucleosynthesis to proceed along pathways far from beta stability, creating extremely neutron-rich isotopes. The R process pathway can reach isotopes near the neutron drip line, where neutrons become unbound and nuclei cannot capture additional neutrons. This creates a natural endpoint for neutron capture, with subsequent beta decay chains converting neutron-rich isotopes into stable heavy elements. The nuclear mass models predict that R-process nucleosynthesis follows specific pathways determined by neutron binding energies and beta decay properties. The waiting point approximation suggests that material accumulates at isotopes with particularly long beta decay half-lives. The neutron density requirements for R-process nucleosynthesis restrict possible astrophysical sites to extremely energetic environments. Core collapse supernovas, neutron star mergers, and magnetar formation events represent the most promising candidates for achieving necessary neutron flux levels. Dr. Chris Snedden's spectroscopic observations of metal-poor stars revealed the signatures of R-process nucleosynthesis in stellar atmospheres. These observations show enhancement patterns consistent with rapid neutron capture, providing observational evidence for RI process operation in early galactic environments. The nuclear reaction networks governing neutron capture nucleosynthesis include thousands of isotopes and hundreds of thousands of nuclear reactions. Modern computational approaches solve these networks numerically to predict abundance patterns under different astrophysical conditions. The neutron capture rates depend on both nuclear cross-sections and neutron energy distributions. Higher neutron energies generally increase capture rates, while neutron energy spectra depend on the temperature and density conditions in the nucleosynthesis environment. The competing nuclear processes during neutron capture nucleosynthesis include neutron-induced fission for the heaviest isotopes and alpha decay for certain neutron-rich species. These processes can terminate neutron capture chains and affect the final abundance distributions. The photodisintegration reactions become important at high temperatures, where energetic photons can reverse neutron capture by photodissociating heavy nuclei. The balance between neutron capture and photodisintegration determines the equilibrium isotope distributions in hot environments. The electron capture processes can affect neutron capture nucleosynthesis in dense environments by by converting protons to neutrons, altering the neutron-to-proton ratio and affecting the available neutron flux for capture reactions. The neutrino interactions with nuclei become significant in core collapse environments, where intense neutrino fluxes can induce nuclear reactions that affect neutron production and heavy element nucleosynthesis patterns. The nuclear deformation effects influence neutron capture cross-sections for heavy nuclei, particularly those approaching spherical or deformed shell closures. These effects must be included in detailed nucleosynthesis calculations to predict accurate abundance patterns. The experimental nuclear physics programs at facilities like the National Superconducting Cyclotron Laboratory and RIKEN provide essential nuclear data for neutron capture nucleosynthesis modeling. Measurements of neutron-rich isotope properties inform theoretical models of R-process pathways. The neutron capture processes ultimately represent the universe's mechanism for building complexity beyond the iron peak, transforming simple neutrons into the complex nuclear structures that comprise the heaviest stable elements while revealing the intricate nuclear physics governing matter under extreme astrophysical conditions. Chapter 5. Rapid Process. The R process, Rapid Neutron Capture Process, represents the universe's most extreme nucleosynthesis mechanism, operating under conditions so violent that neutrons bombard atomic nuclei faster than radioactive decay can occur. This process enables the creation of extremely neutron-rich isotopes that subsequently decay into approximately half of all elements heavier than iron, including gold, platinum, and uranium. The fundamental requirement for R-process nucleosynthesis involves neutron densities exceeding 1,020 neutrons per cubic centimeter, roughly 1 billion times denser than water, and approaching the neutron densities found in atomic nuclei. Under these extreme conditions, neutron capture rates become faster than beta decay rates, allowing nucleosynthesis to proceed far from the valley of beta stability. Dr. Margaret Burbage's groundbreaking work in the 1957 BYFH paper first identified the need for rapid neutron capture to explain the observed abundances of neutron-rich heavy isotopes. She recognized that the creation of elements like gold and platinum requires nuclear processes that can build neutron-rich isotopes faster than they can decay, demanding conditions far more extreme than normal stellar environments. The R-process pathway begins with seed nuclei, typically ion group elements created through previous nucleosynthesis processes. Rapid neutron bombardment drives these seed nuclei to increasingly neutron-rich configurations. Adding neutrons much faster than beta decay can convert neutrons to protons. The neutron capture cross-sections for neutron-rich isotopes generally increase with neutron excess, facilitating rapid neutron addition. Unlike stable nuclei, which often have small neutron capture cross-sections, unstable neutron-rich isotopes typically exhibit large capture cross-sections exceeding 101,000 millibarns. The nuclear flow pattern during R-process nucleosynthesis follows contours of constant neutron binding energy rather than the valley of beta stability. Material flows rapidly to neutron-rich regions where neutron binding energies become small, creating quasi-equilibrium between neutron capture and photodisintegration. Dr. Friedrich Karl Thielmann from the University of Basel, whose R-process calculations span decades of research, explains that a process nucleosynthesis operates in a regime where neutron capture and photodisintegration maintain quasi-equilibrium, with nuclear flows determined by neutron binding energies rather than beta stability considerations. The waiting point approximation provides insight into R-process dynamics by identifying isotopes where beta decay becomes rate limiting. These waiting points occur at isotopes with very small neutron binding energies or particularly long beta decay half-lives, causing material accumulation that affects final abundance patterns. The neutron drip line represents the ultimate boundary for neutron capture. beyond which neutrons become unbound and cannot be retained by atomic nuclei. Our process nucleosynthesis can approach this boundary, creating isotopes with neutron-to-proton ratios exceeding 2.5 for heavy elements. The temperature requirements for I-process nucleosynthesis range from 0.5 to 2.0 million Kelvin, hot enough to maintain neutron capture, photodisintegration, equilibrium but cool enough to prevent complete nuclear disintegration. This narrow temperature window restricts possible astrophysical sites. Determination of I-process nucleosynthesis occurs through several mechanisms: neutron exhaustion, expansion cooling, or fission cycling for the heaviest elements. Spontaneous fission becomes inevitable for isotopes heavier than mass number 270 to 280, creating a natural upper limit for I-process production. The nuclear mass measurements provide essential input for I-process calculations by determining neutron binding energies and reaction rates. Modern mass spectrometry techniques can measure masses of neutron-rich isotopes with uncertainties below 10 keV, enabling precise nucleosynthesis modeling. Dr. Bradley Sherrill's experimental program at the National Superconducting Cyclotron Laboratory produces neutron-rich isotopes for nuclear physics studies relevant to I-process nucleosynthesis. These experiments measure nuclear properties that cannot be calculated reliably from theory alone. The astrophysical sites for I-process nucleosynthesis remain debated, with core collapse supernovas and neutron star mergers representing the leading candidates. Both environments can potentially achieve the extreme neutron densities and temperatures required for rapid neutron capture. The neutrino-driven wind model for core collapse supernovas proposes that neutrino heating of material above the protoneutron star creates neutron-rich outflows with conditions suitable for I-process nucleosynthesis. The neutron-to-proton ratio in these winds depends on neutrino interaction rates and explosion dynamics. Dr. Gabriel Martinez-Pinedo's calculations of neutrino wind nucleosynthesis reveal the complex nuclear physics governing I-process conditions in supernovas. The competition between neutrino capture on protons and neutrons determines the neutron excess available for heavy element production. The neutron star merger scenario gained observational support with the 2017 detection of gravitational waves from GW170817, accompanied by electromagnetic counterparts consistent with I-process nucleosynthesis. The optical and infrared observations showed signatures of heavy element production in the merger ejecta. The kilonova emission from neutron star mergers results from radioactive decay of I-process elements, particularly lanthanides and actinides that exhibit complex atomic structure, creating broad absorption features. These observations provide direct evidence for heavy element synthesis in merger environments. Dr. Brian Metzger's models of neutron star merger ejecta demonstrate how tidal disruption and shock heating can create multiple components of I-process material with different neutron densities and temperatures. The diversity of ejecta conditions enables production of the full range of I-process elements. The magnetorotational explosions of massive stars represent another potential I-process site, where strong magnetic fields and rapid rotation create jets and disk winds that might achieve necessary neutron densities. These events could explain I-process enhancement in certain stellar populations. The nuclear reaction networks for I-process nucleosynthesis include over 5,000 isotopes and millions of nuclear reactions, requiring sophisticated computational techniques to solve. The reaction rates depend on nuclear masses, capture cross-sections, beta decay half-lives, and fission properties. The uncertainty quantification in I-process calculations addresses how nuclear physics uncertainties affect predicted abundance patterns. Monte Carlo approaches vary nuclear properties within experimental uncertainties to determine the sensitivity of nucleosynthesis outcomes to specific nuclear parameters. The nuclear fission process becomes crucial for the heaviest R process isotopes, where spontaneous and neutron-induced fission rates determine the maximum mass reached during neutron capture. The fission fragment distributions affect the final abundance patterns of heavy elements. The superheavy element research provides insights into raw process termination mechanisms by measuring fission properties of very heavy isotopes. These experiments reveal how nuclear stability decreases with increasing mass number, confirming theoretical predictions about R process endpoints. The beta decay properties of neutron-rich isotopes determine R process timescales and waiting point locations. Theoretical calculations and experimental measurements of beta decay half-lives provide essential input for all nucleosynthesis modeling. The stellar archaeology approach uses observations of metal-poor stars to study early reprocessed nucleosynthesis. These ancient stars preserve abundance patterns from individual R process events that occurred during early galactic evolution, providing constraints on R process sites and yields. Dr. Anna Frebel's observations of ultra-metal-poor stars reveal R process enhancement patterns consistent with nucleosynthesis in low-mass neutron star mergers or rare supernova events. These observations suggest that early R process production occurred in relatively few high-yield events. The galactic chemical evolution models incorporate R process nucleosynthesis to predict heavy element abundance patterns throughout galactic history. These models must account for the rarity of R process sites and the delay times between star formation and heavy element production. The cosmic ray studies provide additional constraints on R process nucleosynthesis through measurements of radioactive isotopes like thorium-232 and uranium-238. The observed isotope ratios reflect the time-integrated history of raw process element production in the galaxy. The laboratory nuclear physics experiments using radioactive beam facilities create neutron-rich isotopes similar to those involved in raw process nucleosynthesis. These experiments measure nuclear properties that determine reaction rates and pathways during rapid neutron capture. The theoretical nuclear models predict properties of neutron-rich isotopes that cannot be measured experimentally due to their short half-lives. Density functional theory and shell model calculations provide neutron binding energies and decay properties for nucleosynthesis modeling. The R process nucleosynthesis ultimately represents nature's most extreme nuclear alchemy, converting neutrons into the complex nuclear architectures that comprise the universe's heaviest elements while operating under conditions that approach the fundamental limits of nuclear stability and reaction physics. Chapter 6. Heavy Creation. The creation of the universe's heaviest elements. Gold, platinum, uranium, and their neighbors in the periodic table requires nuclear processes so extreme they operate at the very limits of atomic stability. These elements represent the ultimate products of cosmic nucleosynthesis, forged through rapid neutron capture in environments where nuclear physics approaches its theoretical boundaries. Gold 197 contains 79 protons and 118 neutrons, exemplifies the nuclear complexity required for heavy element creation. This isotope cannot be produced through any sequence of charged particle reactions because the Coulomb barriers become insurmountable long before reaching such high atomic numbers. Only neutron capture processes can build nuclei with nearly 200 nucleons. Dr. John Cowan from the University of Oklahoma, whose spectroscopic observations revealed Rye process elements in metal-poor stars, explains that gold represents a nuclear architecture that pushes atomic structure to extreme limits. The electromagnetic repulsion between 79 protons creates internal stresses that require precisely balanced nuclear forces to maintain stability. The neutron-to-proton ratios in heavy R process isotopes approach 2.5 to 1, far exceeding the 1.5 to 1 ratios typical for stable heavy elements. These extreme neutron excesses indicate that heavy element creation occurs through processes that drive nuclei far from stability before beta decay chains convert neutron-rich precursors into stable products. The nuclear binding energies of heavy elements reveal the delicate balance maintaining nuclear stability. Uranium-238, with a binding energy of 7.6 million electron volts per nucleon, approaches the limit where electromagnetic repulsion nearly overcomes nuclear attraction. Heavier elements become increasingly unstable due to Coulomb energy growth. The alpha decay process becomes inevitable for the heaviest elements as Coulomb repulsion creates favorable energetics for alpha particle emission. Elements heavier than lead predominantly decay through alpha emission, releasing helium-4 nuclei to reduce nuclear charge and approach more stable configurations. The fission barriers of heavy elements determine their stability against spontaneous fission. Uranium-238 has a fission barrier of approximately 6 million electron volts, while heavier elements have progressively lower barriers that eventually reach zero for superheavy isotopes. Dr. Witold Nazarovich from Michigan State University, whose theoretical work addresses nuclear stability limits, notes that heavy element creation pushes nuclear physics into regimes where quantum shell effects, Coulomb repulsion, and nuclear surface tension compete to determine stability. The heaviest stable elements represent optimal compromises between these competing forces. The R-process production of heavy elements requires neutron capture chains that add 4080. Neutrons to seed nuclei before beta decay can convert neutron excess into additional protons. This massive neutron addition demands neutron fluxes exceeding anything available during normal stellar evolution. The nuclear flow patterns during heavy element creation follow pathways determined by neutron binding energies and beta decay properties. Material accumulates at waiting points where neutron binding energies become small or beta decay half-lives become long, creating characteristic abundance patterns. The lanthanide elements' atomic numbers 57 to 71 exhibit particularly complex nuclear structure due to the filling of 4f electron orbitals combined with neutron shell effects. These elements require R-process neutron capture to bridge the stability gap between lighter and heavier isotopes. The actinide elements, atomic numbers 89 to 103, represent the heaviest naturally occurring elements, with uranium-238 and thorium-232 being the only long-lived isotopes remaining from primordial nucleosynthesis. These elements decay through complex chains involving multiple alpha and beta decays. The nuclear data requirements for modeling heavy element creation include masses, neutron capture cross-sections, beta decay half-lives, and fission properties for thousands of neutron-rich isotopes. Many of these properties cannot be measured experimentally due to short isotope lifetimes. Dr. Toshitaka Kajino from the University of Tokyo, whose research addresses heavy element nucleosynthesis, explains that creating elements like platinum and gold requires nuclear reaction networks involving over 3,000 isotopes, most of which exist for only milliseconds and cannot be produced in terrestrial laboratories. The neutron separation energies determine how easily neutrons can be added to heavy nuclei during R-process nucleosynthesis. These energies decrease systematically as nuclei become more neutron-rich, eventually approaching zero at the neutron drip line. The beta decay Q values determine the energy release during neutron-to-proton conversion and affect beta decay rates through phase space considerations. Large Q values accelerate beta decay and can terminate neutron capture chains before reaching the heaviest elements. The astrophysical conditions required for heavy element creation involve not only extreme neutron densities, but also specific entropy and expansion timescales. Too rapid expansion prevents sufficient neutron captures, while too slow expansion allows beta decay to compete with neutron capture. The freeze-out process terminates heavy element creation when neutron densities drop below critical thresholds or temperatures become too low for continued nuclear reactions. The timing of freeze-out determines which isotopes complete their neutron capture before beta decay converts them to final products. The neutron-star merger calculations reveal complex hydrodynamics governing heavy element production in these events. The tidal disruption creates neutron-rich material with varying conditions throughout the ejecta, enabling production of the full range of heavy elements. Dr. Francois Foucault's numerical simulations of neutron star mergers demonstrate how gravitational interactions create multiple ejecta components with different neutron densities. The diversity of conditions enables comprehensive heavy element production from a single merger event. The kilonova observations provide direct evidence for heavy element creation through the detection of optical and infrared emission powered by radioactive decay. The broad absorption features indicate the presence of lanthanides and actinides with complex atomic structure. The nuclear cosmochronometry uses radioactive isotopes like uranium-238, thorium-232, and rhenium-187 to determine the age of heavy elements and constrain Rye process production rates throughout galactic history. These natural clocks provide timestamps for nucleosynthesis events. The galactic enrichment patterns show that heavy element abundances increase systematically from the galactic halo toward the disk, reflecting the gradual buildup of R process elements through merger events and rare supernova explosions throughout cosmic time. The chemical evolution models must account for the rarity and high yields of process events to reproduce observed heavy element abundance patterns. The model suggests that individual neutron star mergers, or rare supernovas, can enrich large volumes of interstellar material. The stellar absorption line observations reveal heavy element abundance patterns in stellar atmospheres that preserve signatures of individual R process events. Metal-poor stars show either R process enhancement or deficiency, indicating that heavy element production occurs in rare, high-yield events. Dr. Christopher Snedden's extensive spectroscopic surveys have identified hundreds of process-enhanced stars that preserve abundance patterns from early heavy element production. These observations constrain the masses and yields of process sources in the early galaxy. The meteorite studies provide detailed heavy element abundance patterns that reflect the integrated history of nucleosynthesis in the solar system's formation region. Isotopic anomalies in meteorites preserve signatures of individual stellar nucleosynthesis events. The superheavy element research pushes heavy element creation to its absolute limits by synthesizing elements with atomic numbers exceeding 110. These elements exist for only milliseconds, but provide insights into nuclear stability limits and potential islands of enhanced stability. The theoretical predictions suggest that superheavy elements around atomic number 114 and neutron number 184 might exhibit enhanced stability due to quantum shell effects. However, even these stable superheavy elements would have half-lives measured in minutes rather than geological timescales. The nuclear liquid drop model predicts that elements heavier than atomic number 106 should undergo spontaneous fission almost instantly, but quantum shell effects can significantly enhance stability for specific proton and neutron combinations. The experimental synthesis of superheavy elements at facilities like GSI, Riken, and Dubna requires bombarding heavy target nuclei with lighter projectiles to overcome Coulomb barriers and create fusion products. The production cross-sections become vanishingly small for the heaviest elements. The heavy element abundance patterns in the solar system reflect the integrated contributions from multiple R process events throughout galactic history. The relative abundances provide constraints on R process sites, yields, and frequency throughout cosmic evolution. The nuclear astrophysics experiments using radioactive beam facilities attempt to measure nuclear properties relevant to warp process nucleosynthesis. These experiments probe neutron-rich isotopes under conditions that approximate astrophysical environments. The heavy element creation ultimately represents the universe's most sophisticated nuclear engineering, building complex atomic architectures that approach the fundamental limits of nuclear stability while creating the chemical diversity that enables technological civilization and, potentially, biological complexity throughout the cosmos. Chapter 7. Cosmic Distribution. The violent deaths of massive stars launch freshly synthesized heavy elements into space at velocities exceeding 10,000 kilometers per second, creating expanding shells of enriched material that seed the interstellar medium with chemical complexity. This cosmic distribution process determines where and when heavy elements become available for incorporation into subsequent generations of stars and planets. The supernova blast wave propagates through the surrounding interstellar medium at hypersonic velocities, creating shock-heated regions where heavy elements mix with ambient hydrogen and helium. The shock front can maintain velocities of several thousand kilometers per second for thousands of years, distributing nucleosynthesis products across volumes exceeding 1,000 cubic parsecs. Dr. Robert McCrae from the University of Colorado, whose models address supernova remnant evolution, explains that supernovas function as cosmic element distributors, not only creating heavy elements but launching them into space where they become incorporated into the galactic ecosystem of star formation and chemical evolution. The mass ejection from core collapse supernovas typically ranges from 10 to 20 solar masses, with heavy element yields of 0.1 to 1.0 solar masses per explosion. This material contains the products of both hydrostatic nucleosynthesis during stellar evolution and explosive nucleosynthesis during the supernova event itself. The velocity structure of supernova ejecta shows systematic variations with composition, reflecting the layered structure of massive stars at the time of explosion. The innermost ejecta, containing freshly synthesized heavy elements, typically achieves the highest velocities due to energy input from the explosion shock. The mixing processes during supernova explosions significantly affect element distribution patterns. Rayleigh-Taylor instabilities and convective mixing can transport heavy elements from inner zones to outer ejecta layers, altering the expected onion shell structure of pre-explosion stellar composition. Dr. Adam Burrows from Princeton University, whose three-dimensional supernova simulations reveal explosion asymmetries, notes that real supernovas are inherently asymmetric events with complex mixing patterns that affect how different elements are distributed throughout the ejecta and into the surrounding medium. The neutron star kicks imparted during core collapse can reach velocities exceeding 1,000 kilometers per second, reflecting the asymmetric nature of the explosion process. These kicks indicate momentum transfer that affects the distribution of heavy elements around explosion sites. The supernova light curves provide observational evidence for explosive nucleosynthesis through the radioactive decay of freshly synthesized isotopes. The decay of nickel-56 to cobalt-56 to iron-56 powers the optical emission for months after explosion, confirming iron peak element production. The spectroscopic observations of supernova ejecta reveal heavy element abundance patterns and velocity distributions. Late-time spectra show emission lines from iron, nickel, and intermediate mass elements moving at thousands of kilometers per second relative to the explosion center. The supernova remnant observations using X-ray telescopes revealed a long-term evolution of heavy element distribution. Young remnants like Cassiopeia A show clear evidence for freshly synthesized titanium, chromium, manganese, iron, nickel, and trace amounts of heavier elements. The Chandra X-ray Observatory's high-resolution images of supernova remnants reveal detailed maps of heavy element distribution, showing how different elements occupy different regions within expanding remnants. These observations confirm theoretical predictions about explosive nucleosynthesis zones Dr. Una Huang from NASA Goddard Space Flight Center, whose X-ray observations reveal heavy element distributions in supernova remnants, explains that we can literally see the products of stellar nucleosynthesis distributed throughout expanding shockwaves, providing direct evidence for how stars create and distribute heavy elements. The interstellar medium enrichment occurs through multiple mechanisms beyond direct supernova injection. Stellar winds from massive stars contribute heavy elements before explosion, while supernova shock waves can trigger star formation that accelerates chemical enrichment processes. The superbubble formation results from multiple supernova explosions in star-forming regions, creating large cavities in the interstellar medium filled with hot, metal-enriched gas. These superbubbles can extend for hundreds of parsecs and significantly affect galactic chemical evolution. The galactic fountain model describes how supernova explosions drive metal-enriched gas into galactic halos, where it cools and eventually falls back onto galactic disks. This recycling process distributes heavy elements both spatially and temporally throughout galactic evolution. The metallicity gradients observed in spiral galaxies reflect the inside-out formation of galactic disks, combined with radial variations in star formation rates and supernova frequencies. Inner galactic regions show enhanced heavy element abundances due to higher stellar densities and more efficient element retention. Dr. Ken Freeman from the Australian National University, whose observations revealed metallicity gradients in galactic disks, notes that the radial distribution of heavy elements in galaxies provides a fossil record of how supernovas have enriched different galactic regions. Throughout cosmic history, the local bubble surrounding our solar system represents a superbubble created by multiple supernova explosions in the local stellar neighborhood over the past 10 to 20 million years. This cavity contains hot, tenuous gas with enhanced abundances of elements created through stellar nucleosynthesis. The cosmic ray acceleration in supernova shock fronts provides another mechanism for heavy element distribution. Shock-accelerated heavy nuclei can travel throughout galaxies, carrying nucleosynthesis signatures across vast distances before being detected in cosmic ray experiments. The isotopic signatures in cosmic rays preserve information about nucleosynthesis processes in source regions. The ratios of different isotopes reflect the mix of contributions from various stellar sources and provide constraints on galactic chemical evolution models. The molecular cloud enrichment occurs when supernova shock waves encounter dense interstellar clouds, compressing them while injecting heavy elements that become incorporated into subsequent star formation episodes. This process links stellar death directly to stellar birth. The triggered star formation in molecular clouds compressed by supernova shock waves can create positive feedback loops where stellar death promotes stellar birth. The newly formed stars inherit enhanced heavy element abundances from previous nucleosynthesis episodes. Dr. Bruce Elmgreen from IBM Research, whose work addresses triggered star formation, explains that supernova explosions create a complex ecology where stellar death feeds stellar birth, gradually increasing the heavy element content available for planet formation and potentially biological evolution. The galactic winds driven by supernova explosions can either enhance element mixing or remove heavy elements from star-forming regions entirely. The balance between enrichment and loss depends on galaxy mass, star formation rate, and the efficiency of supernova energy coupling. The dwarf galaxy observations reveal how supernova feedback affects small galactic systems. Low-mass galaxies can lose significant fractions of their heavy elements through supernova-driven winds, creating metallicity patterns that differ from massive spirals. The intracluster medium enrichment results from galactic winds and tidal stripping that distribute heavy elements throughout galaxy clusters. X-ray observations reveal iron abundances exceeding solar values in hot gas between cluster galaxies. The redshift evolution of heavy element abundances traces cosmic chemical evolution from early universe, conditions dominated by hydrogen and helium, to the current epoch where heavy elements comprise several % of cosmic material by mass. The damped Lyman alpha systems observed in quasar spectra provide measurements of heavy element abundances at high redshift, revealing how cosmic chemical enrichment has proceeded throughout the majority of cosmic history. Dr. Jason Prohaska from UC Santa Cruz, who surveys probe cosmic chemical evolution, notes that the cosmic abundance evolution shows systematic increases in heavy element content from early times to the present, reflecting the cumulative effects of stellar nucleosynthesis throughout cosmic history. The chemical abundance patterns in different stellar populations preserve records of element production and distribution at different cosmic epochs. Population 2 stars in the galactic halo show the signatures of early chemical enrichment, while population I disk stars reflect more recent nucleosynthesis. The solar system formation incorporated heavy elements distributed by previous generations of stellar death, creating the chemical diversity that enables rocky planet formation and potentially biological evolution. The solar abundance patterns reflect the integrated history of nucleosynthesis in the local galactic environment. The Brazolo grains preserved in meteorites carry isotopic signatures from individual stellar sources, providing direct samples of material created through stellar nucleosynthesis and distributed through supernova explosions or stellar winds. The galactic archaeology approach uses stellar spectroscopy to reconstruct the chemical evolution history of the Milky Way by analyzing abundance patterns in stars of different ages and galactic locations. This technique reveals how element distribution has evolved throughout galactic history. The numerical simulations of galactic chemical evolution incorporate supernova yields, stellar evolution timescales, and gas dynamics to predict heavy element distribution patterns. These models must account for the stochastic nature of supernova explosions and their effects on local enrichment. The cosmic distribution of heavy elements ultimately determines where complex chemistry becomes possible throughout the universe, creating conditions where rocky planets can form and technological civilizations might develop, while revealing the intimate connections between stellar death and cosmic evolution. Chapter 8. Galactic Enrichment. Gradual enrichment of galaxies with heavy elements created through stellar nucleosynthesis represents one of the universe's most profound transformation processes, converting primordial hydrogen and helium into the chemical complexity necessary for rocky planet formation and potentially biological evolution. This galactic chemical evolution operates over billions of years, fundamentally altering the cosmic environment. The primordial universe emerging from Big Bang nucleosynthesis contained approximately 75% hydrogen, 25% helium, and trace amounts of lithium, beryllium, and boron. Heavier elements existed at negligible levels, meaning the early universe lacked the chemical diversity necessary for forming dust grains, rocky planets, or complex molecular chemistry. Dr. Bernard Pagel from the University of Sussex, whose pioneering work established galactic chemical evolution theory, explained that galaxies function as cosmic recycling centers where successive generations of stars gradually convert primordial gas into heavier elements, creating the chemical complexity we observe in the modern universe. The first generation of stars, known as population 3 stars, formed from purely primordial gas compositions lacking heavy elements. These massive stars, potentially reaching 100 to 300 solar masses, lived brief lives ending in spectacular supernova explosions that injected the first heavy elements into the pristine interstellar medium. The nucleosynthesis yields from population 3 supernovas created the initial seed abundance of heavy elements that enabled subsequent generations of stars to form with enhanced metal content. Computer simulations suggest these early supernovas could enrich surrounding gas to metallicities, approaching 0.1% of solar values. The stellar initial mass function determines which stars contribute most significantly to galactic chemical evolution over cosmic time. While massive stars produce the largest amounts of heavy elements per star, intermediate mass stars dominate the overall element production due to their higher formation frequencies. Dr. Francesca Mattucci from the University of Trieste, whose galactic evolution models span decades of research, notes that galactic chemical evolution represents a balance between element production through stellar nucleosynthesis, element distribution through stellar winds and supernovas, and element loss through galactic outflows. The supernova rates throughout galactic history determine the pace of heavy element injection into interstellar gas. Type II supernovas from massive stars dominate during early galactic evolution, while Type Ia supernovas from white dwarf binaries contribute significantly during later epochs with characteristic delay times. The star formation history of galaxies controls chemical evolution timescales by determining when stellar populations form and how quickly they process gas into stars. Galaxies with extended star formation histories show gradual metallicity increases, while starburst galaxies achieve rapid enrichment followed by quiescence. The gas infall and outflow processes significantly affect galactic chemical evolution by adding metal-poor material and removing metal-enriched gas. The balance between these processes determines whether galaxies retain their nucleosynthesis products or lose them to intergalactic space. The metallicity gradients observed in spiral galaxy disks reflect inside-out disk formation combined with radial variations in star formation efficiency. Intergalactic regions typically show metallicities 2 to 3 times higher than outer regions due to higher stellar densities and more efficient gas retention. Dr. Fabio Brissan's stellar evolution calculations reveal how different stellar masses contribute various elements to galactic enrichment. Low-mass stars produce carbon and nitrogen through asymptotic giant branch evolution, while massive stars create oxygen, silicon, and iron peak elements. The alpha element enhancement patterns in old stellar populations reflect early galactic evolution, when Type II supernovas dominated heavy element production. The alpha to iron ratios decrease over time as Type Ia supernovas contribute increasing amounts of iron peak elements with longer delay times. The R process and S process element production occurs through different stellar sources with distinct timescales, creating complex abundance patterns that evolve differently throughout galactic history. Neutron star mergers and rare supernovas produce R process elements, while GB stars create SAR process elements. The observational evidence for galactic chemical evolution comes from stellar spectroscopy that measures elemental abundances in stars of different ages and metallicities. These observations reveal systematic abundance patterns that constrain models of stellar nucleosynthesis and galactic evolution. The Hipparcos and Gaia space missions provide precise stellar distances and ages that enable detailed studies of chemical evolution in the solar neighborhood. These data reveal how metallicity and abundance ratios have evolved over the past 10 billion years of galactic history. Dr. Sophia Feltzing from Lund University, whose studies of stellar populations reveal galactic evolution patterns, explains that stellar abundances provide fossil records of galactic chemical evolution, preserving information about nucleosynthesis processes and element distribution throughout cosmic history. The thick disk and thin disk components of the Milky Way show distinct chemical signatures reflecting different formation epochs and enrichment histories. The thick disk formed earlier with rapid enrichment, while the thin disk shows more gradual evolution with extended star formation. The galactic halo populations preserve signatures of early chemical evolution when the galaxy formed through mergers of smaller systems. The most metal-poor halo stars show abundance patterns reflecting nucleosynthesis in massive population, 3 stars, and early chemical enrichment episodes. The dwarf galaxy observations reveal how galaxy mass affects chemical evolution through supernova feedback and gas retention efficiency. Low-mass galaxies experience more dramatic chemical evolution due to their shallow gravitational potential wells and susceptibility to gas loss. The local group dwarf spheroidal galaxies show truncated star formation histories and low current metallicities, indicating that supernova feedback terminated their chemical evolution early in cosmic history. These systems preserve records of ancient nucleosynthesis processes. Dr. Aline Tolstoy from the University of Groningen, whose observations probe chemical evolution in dwarf galaxies, notes that small galaxies provide crucial tests of chemical evolution models because their simple star formation histories and clear observational signatures reveal fundamental nucleosynthesis and feedback processes. The intracluster medium observations using X-ray telescopes reveal heavy element abundances that reflect the integrated chemical evolution of entire galaxy clusters. The iron abundance in hot cluster gas approaches solar values, indicating efficient element distribution from cluster galaxies. The high redshift galaxy observations using space telescopes probe chemical evolution during earlier cosmic epochs when the universe was 1 to 3 billion years old. These observations reveal surprisingly high metallicities in some early galaxies, indicating rapid chemical enrichment processes. The damped Lyman alpha absorbers in quasar spectra provide measurements of heavy element abundances in high redshift galaxies that are too faint for direct spectroscopic observations. These systems show metallicity evolution from early times to the present epoch. The cosmic star formation rate evolution determines the global pace of chemical enrichment throughout cosmic history. The star formation rate peaked when the universe was 2 to 3 billion years old, coinciding with the epoch of maximum chemical evolution activity. Dr. Piromado's studies of cosmic star formation history revealed that the universe has processed approximately 5% of its baryonic material through stars since the Big Bang, converting significant fractions of primordial hydrogen and helium into heavier elements through stellar nucleosynthesis. The galactic winds and outflows play crucial roles in chemical evolution by removing metal-enriched gas from galaxies and potentially redistributing it to larger scales. These processes can either enhance mixing or cause net heavy element loss depending on galaxy properties. The chemical evolution models must account for complex gas dynamics, stellar feedback, and environmental effects that influence star formation and element retention. Modern simulations include magnetic fields, cosmic rays, and black hole feedback to reproduce observed abundance patterns. The isotopic ratios in galactic chemical evolution provide additional constraints on nucleosynthesis processes and timescales. Different stellar sources produce distinct isotopic signatures that can be traced through spectroscopic observations of stellar abundances. The planetary nebula abundances reveal the products of intermediate mass star nucleosynthesis and provide observational constraints on stellar evolution models. These objects show enhanced nitrogen and helium abundances, reflecting nuclear burning during asymptotic giant branch evolution. The supernova remnant observations provide direct evidence for ongoing galactic chemical enrichment by revealing freshly synthesized elements distributed throughout expanding shock waves. These observations confirm theoretical predictions about explosive nucleosynthesis yields. The galactic fountain model describes how supernova explosions launch metal-enriched gas into galactic halos, where it cools and falls back onto galactic disks over timescales of 100 million years. This process distributes heavy elements both spatially and temporally. The chemical evolution of the solar neighborhood reveals systematic increases in metallicity over the past 10 billion years, with current star-forming regions showing metallicities 2 to 3 times higher than the oldest stellar populations in the galactic disk. The galactic enrichment process ultimately transforms galaxies from metal-poor systems dominated by hydrogen and helium into chemically complex environments where heavy elements comprise several percent of the total mass, enabling the formation of dusty, rocky planets and potentially the complex molecular chemistry necessary for biological evolution. Chapter 9. Observable Signatures. The nuclear furnaces operating inside exploding stars leave distinctive fingerprints throughout the observable universe, creating measurable signatures that confirm theoretical predictions about heavy element creation. These observational evidences span multiple astronomical techniques, from spectroscopy of individual stars to gravitational wave detections from merging neutron stars. The spectroscopic observations of stellar atmospheres provide the most direct evidence for stellar nucleosynthesis by revealing elemental abundance patterns that reflect nuclear burning processes. High-resolution spectrographs can measure abundances for dozens of elements with precisions better than 10%, enabling detailed comparisons with theoretical nucleosynthesis predictions. Dr. Christopher Snedden from the University of Texas at Austin, whose spectroscopic surveys span decades of heavy element research, explains that stellar atmospheres preserve chemical fingerprints from individual nucleosynthesis events, allowing us to reconstruct the history of element production throughout galactic evolution. The metal poor star observations reveal abundance patterns from early galactic chemical evolution when individual nucleosynthesis events could significantly affect local chemical compositions. These stars show either enhancement or deficiency in raw process elements, indicating that heavy element production occurs in rare, high-yield events. The R-process enhanced stars exhibit abundance patterns consistent with rapid neutron capture nucleosynthesis, showing systematic enhancements of elements like europium, gadolinium, and gold relative to iron. These abundance signatures provide observational confirmation for R-process theory and constraints on astrophysical sites. The neutron capture element ratios in stellar spectra reveal the contributions of different nucleosynthesis processes. The europium to barium ratio distinguishes R-process from SIF process contributions, while thorium and uranium abundances provide nuclear cosmochronometry for determining stellar ages. Dr. Anna Frebel from MIT, whose ultra-metal poor star discoveries probe early chemical evolution, notes that the most ancient stars in our galaxy preserve abundance patterns from the first episodes of heavy element creation, revealing how R-process nucleosynthesis operated when the universe was young. The supernova light curve observations provide direct evidence for explosive nucleosynthesis through the radioactive decay of freshly synthesized isotopes. The optical emission from Type Ia supernovas is powered by nickel-56 decay, while core collapse events show signatures from multiple radioactive species. The late-time supernova spectra reveal emission lines from iron, nickel, and intermediate mass elements moving at thousands of kilometers per second. These observations confirm theoretical predictions about explosive burning zones and element distribution within supernova ejecta. The gamma-ray observations of supernova remnants detect the characteristic emission lines from radioactive decay of nucleosynthesis products. The 1.809 MeV line from aluminum-26 decay reveals ongoing nucleosynthesis in star-forming regions throughout the galaxy. The X-ray observations using space telescopes like Chandra and X and Manhattan reveal heavy element distributions in supernova remnants with unprecedented spatial resolution. These observations show how different elements occupy distinct regions within expanding remnants, confirming explosion models. Dr. Carl Badines from the University of Pittsburgh, whose X-ray studies reveal supernova nucleosynthesis signatures, explains that we can literally map the products of stellar nuclear burning distributed throughout supernova remnants, providing direct observational tests of nucleosynthesis theory. The kilonova observations from neutron star mergers provide spectacular confirmation of R-process nucleosynthesis in these events. The optical and infrared emission shows broad absorption features characteristic of lanthanides and actinides created through rapid neutron capture. the GW170817 gravitational wave detection, followed by electromagnetic observations across the spectrum, represents a watershed moment in nuclear astrophysics. The optical transient showed signatures of heavy element synthesis, while the gravitational waves confirmed the neutron star merger trigger. The nucleosynthesis signatures in kilonova spectra include broad absorption features from lanthanide elements with complex atomic structure. The observed colors and light curve evolution match theoretical predictions for RSS element decay heating. Dr. Ido Berger from Harvard University, whose team observed the electromagnetic counterpart to GW170817, notes that the kilonova observations provide direct confirmation that neutron star mergers create significant amounts of heavy elements, resolving decades of debate about mirror process sites. The cosmic ray observations provide additional evidence for stellar nucleosynthesis through measurements of isotopic ratios that reflect nuclear burning processes. The ratios of neon isotopes and other species preserve signatures from different stellar sources throughout the galaxy. The Brizola grain studies in meteorites reveal isotopic signatures from individual stellar nucleosynthesis events preserved in microscopic particles that condensed in stellar atmospheres before solar system formation. These grains provide direct samples of stellar nucleosynthesis products. The silicon carbide grains found in meteorites show isotopic patterns characteristic of asymptotic giant branch star nucleosynthesis, while silicon nitride grains may preserve signatures from supernova explosions. These observations provide ground truth for stellar evolution models. Dr. Larry Nittler from Arizona State University, whose Brizola grain research reveals stellar nucleosynthesis signatures, explains that meteorites contain microscopic fossils of stellar death that preserve isotopic fingerprints from individual nucleosynthesis events, providing unique constraints on stellar evolution theory. The galactic chemical evolution observations reveal systematic trends in elemental abundances that reflect the cumulative effects of stellar nucleosynthesis throughout cosmic history. The metallicity gradients in spiral galaxies provide observational tests of chemical evolution models. The abundance ratio patterns in stellar populations reveal the relative contributions of different nucleosynthesis sources over time. The alpha to iron ratios trace the transition from type II to type Ia supernova dominance, whilst process element patterns reflect a GB star contributions. The high redshift galaxy observations using space telescopes probe chemical evolution during early cosmic epochs when heavy element abundances were much lower than current values. These observations reveal surprisingly rapid chemical enrichment in some early systems. The damped Lyman alpha absorption systems in quasar spectra provide measurements of heavy element abundances at various cosmic epochs, revealing the evolution of galactic metallicity from early times to the present day. Dr. Max Pettini from the University of Cambridge, whose high redshift abundance measurements probe cosmic chemical evolution, notes that observations of distant galaxies reveal how the universe gradually accumulated heavy elements through stellar nucleosynthesis over billions of years of cosmic evolution. The infrared observations of dust extinction and emission reveal heavy element abundances through the detection of silicate and carbonaceous dust grains created from stellar nucleosynthesis products. Dust-to-gas ratios provide independent metallicity estimates. The planetary nebula observations show the products of intermediate mass star nucleosynthesis distributed through ionized gas shells around central white dwarf stars. These observations reveal enhanced carbon, nitrogen, and oxygen abundances from asymptotic giant branch burning. The Wolf-Rayet star observations reveal extreme stellar wind mass loss that exposes nuclear burning products at stellar surfaces. These stars show surface compositions dominated by helium, carbon, and oxygen burning products, confirming massive star evolution models. The brown dwarf observations provide tests of stellar evolution theory for very low-mass objects that never achieve significant nuclear burning. The lack of heavy element enhancement in brown dwarf atmospheres confirms that substantial nucleosynthesis requires stellar mass cores. Dr. Kelvin from Penn State University, whose brown dwarf surveys probe low-mass stellar evolution, explains that brown dwarfs serve as control experiments for stellar nucleosynthesis because they preserve primordial compositions without significant nuclear processing. The white dwarf observations reveal the final products of stellar evolution for low and intermediate mass stars. The surface compositions of white dwarfs reflect nuclear burning histories, while cooling ages provide constraints on galactic evolution timescales. The neutron star observations through pulsar timing and X-ray spectroscopy reveal extreme matter under conditions that approximate stellar core collapse, environments where heavy elements are created. These observations constrain nuclear physics relevant to nucleosynthesis. The black hole observations provide insights into the most massive stellar evolution endpoints and potential sites for exotic nucleosynthesis processes. The masses and spins of stellar mass black holes preserve information about their massive star progenitors. The gravitational wave astronomy enables studies of compact object mergers that create heavy elements through rare process nucleosynthesis. Future detections will provide statistical samples for understanding merger rates and nucleosynthesis yields. The laboratory nuclear physics experiments using radioactive beam facilities measure nuclear properties relevant to stellar nucleosynthesis. These experiments provide reaction rates and decay properties for isotopes that cannot be studied through astronomical observations. The theoretical nuclear physics calculations predict properties of exotic isotopes involved in nucleosynthesis processes. Density functional theory and shell model calculations provide nuclear masses and reaction rates for nucleosynthesis modeling. The computational stellar evolution models incorporate detailed nuclear reaction networks to predict nucleosynthesis yields from different stellar masses and metallicities. These models can be directly compared with observational abundance patterns. The galactic chemical evolution simulations combine stellar nucleosynthesis yields with gas dynamics and star formation models to predict abundance patterns throughout galactic evolution. These simulations reproduce observed metallicity gradients and abundance ratio trends. The observable signatures ultimately provide comprehensive confirmation that stars create heavy elements through nuclear burning processes and distribute them throughout the universe via stellar winds and explosive deaths, creating the chemical complexity that enables planetary formation and potentially biological evolution across cosmic scales. Chapter 10. Universal Chemistry. The BO. Heavy elements created through stellar nucleosynthesis and dispersed by supernova explosions have fundamentally transformed the universe's chemical potential, enabling complex molecular chemistry, dust grain formation, and ultimately the rocky planets where technological civilizations might emerge. This cosmic chemical evolution represents one of the universe's most profound transformations. The periodic table beyond iron exists entirely due to stellar death processes, with elements like gold, platinum, uranium, and rare earth metals requiring the extreme neutron fluxes achieved only during supernovas and neutron star mergers. Without these violent cosmic events, the universe would remain forever limited to the simplest chemical combinations. Dr. Virginia Trimble from UC Irvine, whose career spanning stellar nucleosynthesis research, explains that the elements heavier than iron represent cosmic treasures created through stellar violence, transforming a universe dominated by hydrogen and helium into a chemically diverse cosmos capable of supporting complex molecular architectures. The dust grain formation in stellar atmospheres and supernova ejecta requires heavy elements to create the condensation nuclei around which microscopic solid particles can grow. Silicon, magnesium, iron, and other metals form the cores of dust grains that enable gas cooling and subsequent star formation. The molecular complexity in interstellar space depends critically on heavy element abundances, with carbon, oxygen, nitrogen, and sulfur enabling the formation of complex organic molecules including amino acids and nucleic acid bases observed in molecular clouds and meteorites. The planet formation process fundamentally depends on heavy element abundances because rocky planets cannot form without sufficient solid material beyond hydrogen and helium. The minimum metallicity required for terrestrial planet formation corresponds to roughly 10 to 30% of solar heavy element abundances. The habitable zone concept extends beyond simple temperature considerations to include chemical habitability, the presence of sufficient heavy elements to enable rocky planet formation, atmospheric retention, and the complex geochemical cycles that maintain planetary habitability over geological timescales. Dr. Charles Lineweaver from Australian National University, whose research addresses cosmic chemical evolution and habitability, notes that galactic chemical evolution creates a habitability gradient where regions with sufficient heavy element enrichment can support planetary system formation and potentially biological evolution. The technological civilization requirements include access to rare earth elements, platinum group metals, and radioactive elements that enable advanced electronics, catalysis, and nuclear technology. These materials exist only because of R-process nucleosynthesis in stellar explosions and neutron star mergers. The semiconductor industry depends entirely on precisely controlled heavy element compositions, with silicon providing the electronic substrate, while trace amounts of boron, phosphorus, arsenic, and other elements enable the controlled electronic properties essential for modern computation and communication. The catalytic chemistry enabling industrial processes relies heavily on platinum group metals, created through R-process nucleosynthesis. These elements exhibit unique electronic properties that enable selective chemical transformations essential for pharmaceutical production, petroleum refining, and environmental protection. Dr. Andrea Sella from University College London, whose research addresses the chemical significance of heavy elements, explains that modern technology would be impossible without the full range of heavy elements created through stellar nucleosynthesis, from the rare earth magnets in wind turbines to the uranium in nuclear reactors. The biological chemistry utilizes heavy elements in crucial roles despite their low abundances. Iron enables oxygen transport in hemoglobin, zinc activates numerous enzymes, and molybdenum facilitates nitrogen fixation, biological processes that depend on elements created in stellar explosions. The origin of life scenarios increasingly recognize the importance of heavy element availability for enabling the complex chemistry required for self-replicating molecular systems. The iron-sulfur clusters in early metabolic pathways may reflect the cosmic abundance patterns created through stellar nucleosynthesis. The astrobiology implications suggest that complex life may be restricted to cosmic regions and epochs where sufficient heavy element enrichment has occurred through stellar evolution. This creates an astrobiological timeline where complex life becomes increasingly probable as galaxies chemically evolve. The Fermi paradox considerations must account for the galactic chemical evolution timescale that gradually increases heavy element abundances over cosmic time. Early cosmic epochs may have been chemically unsuitable for complex life, regardless of other environmental factors. Dr. Sarah Seeger from MIT, whose research addresses exoplanet atmospheres and habitability, notes that the search for life beyond Earth must consider galactic chemical evolution because planetary atmospheres and surface chemistry depend fundamentally on heavy element availability. The exoplanet observations reveal correlations between host star metallicity and planetary system properties. Metal-rich stars more commonly host giant planets, while super-Earth planets show different metallicity correlations that may reflect distinct formation mechanisms. The atmospheric chemistry of exoplanets depends on heavy element abundances. To create the molecular opacity sources necessary for greenhouse effects, atmospheric dynamics, and potentially biosignatures detectable through spectroscopic observations. The rocky planet composition reflects the heavy element abundances in planet-forming regions, with iron content, silicate mineralogy, and volatile inventories all depending on local nucleosynthesis history preserved in protoplanetary disks. The geochemical cycles operating on terrestrial planets require heavy elements to create the radioactive heating sources that drive plate tectonics, volcanism, and magnetic field generation processes, essential for maintaining planetary habitability over geological time. Dr. Norm Sleep from Stanford University, whose research addresses planetary geophysics and habitability, explains that planetary habitability depends not only on stellar radiation, but on internal heat sources from radioactive decay that enable the geochemical cycles maintaining atmospheric and oceanic chemistry. The magnetic field generation in planetary cores requires metallic iron created through stellar nucleosynthesis. These magnetic fields protect planetary atmospheres from stellar wind erosion and enable the atmospheric retention necessary for surface habitability. The isotopic signatures preserved in meteorites and planetary materials provide detailed records of nucleosynthesis processes operating during solar system formation. These signatures constrain the mixing of material from different stellar sources in the local galactic environment. The Pozzolo grain compositions reveal the diversity of nucleosynthesis sources contributing to solar system formation, including material from asymptotic giant branch stars, supernovas, and potentially neutron star mergers that occurred in the local galactic neighborhood. The solar abundance patterns reflect the integrated nucleosynthesis history of multiple stellar generations that enriched the local interstellar medium before solar system formation. This abundance pattern serves as a reference for understanding galactic chemical evolution. Dr. Katharina Lotters from Washington University, whose work addresses solar system composition and nucleosynthesis, notes that the solar abundance pattern represents a fossil record of stellar nucleosynthesis in the local galactic environment, preserving signatures from multiple generations of stellar death. The galactic metallicity gradients create spatial variations in planetary system properties throughout galaxies. Intergalactic regions with higher metallicities can form more massive rocky planets, while outer regions remain dominated by gas giant formation. The temporal evolution of planetary system properties reflects increasing heavy element abundances over cosmic time. Early planetary systems formed with lower metallicities and different compositions compared to systems forming today. The rare earth element availability becomes crucial for advanced technology development, potentially creating bottlenecks in the evolution of technological civilizations. These elements require specific nucleosynthesis processes that may be rare in the cosmic context. The nuclear technology applications require access to actinide elements like uranium and thorium that exist only because of Rye process nucleosynthesis. The availability of these elements enables both nuclear power generation and nuclear weapons development. The materials science applications utilize the full range of heavy elements to create specialized alloys, superconductors, and other advanced materials with properties impossible to achieve using only light elements. The chemical diversity enabled by heavy elements creates virtually unlimited possibilities for molecular architectures, including the complex organic molecules that may be essential for biological evolution and the synthetic materials enabling technological advancement. The cosmic perspective on chemistry reveals that the universe has evolved from a simple hydrogen-helium system toward increasing chemical complexity through stellar nucleosynthesis processes operating over billions of years of cosmic evolution. The anthropic considerations suggest that conscious observers may only emerge in cosmic regions and epochs where sufficient chemical complexity has developed through stellar death processes. This creates potential selection effects in our observations of cosmic chemical evolution. The future chemical evolution of the universe depends on continued star formation and stellar death processes. But declining gas supplies and changing stellar populations will gradually reduce heavy element production rates over cosmic time. The ultimate fate of cosmic chemistry involves the gradual dispersal of heavy elements through galactic winds, the formation of increasingly metal-rich stellar populations, and eventually the cessation of star formation when gas supplies are exhausted. The universal chemistry created through stellar nucleosynthesis ultimately enables everything from planetary formation to technological civilization, demonstrating how stellar death processes create the chemical foundation for complexity and potentially consciousness throughout the cosmos. Throughout this exploration of cosmic alchemy, we have witnessed how the universe transforms itself through stellar death, converting simple hydrogen and helium into the complex chemical architecture that enables rocky planets, technological civilization, and potentially biological evolution. The story of heavy element creation reveals the profound interconnectedness between stellar violence and cosmic creativity. We began by understanding how stellar factories create elements through nuclear fusion, but discovered their fundamental limitations at the Iron Peak, where nuclear binding energy reaches its maximum. No amount of stellar burning can overcome this nuclear barrier, requiring conditions far more extreme than anything found in normal stellar cores. The explosive death of massive stars creates those extreme conditions, generating temperatures exceeding 10 billion Kelvin and neutron densities approaching nuclear levels. These supernova explosions operate as cosmic nuclear reactors, enabling nuclear processes impossible during peaceful stellar evolution while distributing their products across vast volumes of space. The neutron capture processes reveal how the universe overcomes Coulomb barriers through neutron bombardment that can build the heaviest elements without electromagnetic repulsion. The rapid R process operating during stellar explosions creates extremely neutron-rich isotopes that decay into the stable heavy elements we observe today. The rapid process represents nature's most extreme nucleosynthesis mechanism, creating elements like gold, platinum, and uranium through neutron capture rates that exceed beta decay, pushing nuclear composition far from stability before decay chains convert neutron excess into the complex nuclear architectures of heavy elements. Heavy element creation pushes nuclear physics to its absolute limits, building atomic nuclei containing nearly 200 neutrons and protons while approaching the neutron drip line where nuclear stability breaks down completely. These cosmic forges create the universe's rarest and most complex atomic structures. The cosmic distribution of heavy elements through supernova blast waves and stellar winds determines where chemical complexity becomes available for planet formation. The expanding shells of enriched material seed molecular clouds with the ingredients necessary for rocky world formation and complex molecular chemistry. Galactic enrichment operates over billions of years, gradually transforming galaxies from metal-poor systems, dominated by hydrogen and helium, into chemically diverse environments where heavy elements comprise several percent of total mass. This evolution creates the foundation for technological civilizations. The observable signatures confirm theoretical predictions through multiple independent lines of evidence, from stellar spectroscopy, revealing abundance patterns, to kilonova observations directly witnessing heavy element creation and neutron star mergers. The universe consistently demonstrates that stellar death creates chemical complexity. Universal chemistry, enabled by heavy elements, makes possible everything from semiconductor technology to biological evolution, demonstrating how stellar nucleosynthesis creates the material foundation for complexity and consciousness throughout the cosmos. As you contemplate the origins of matter around you, remember that every element heavier than iron carries the signature of stellar violence. The gold in jewelry, the silver in electronics, The uranium in nuclear reactors, and the rare earth elements in smartphones all originated in explosions so powerful they could outshine entire galaxies. Consider the profound rarity of heavy element creation. The elements enabling technological civilization require nuclear processes so extreme. They operate only during the most catastrophic events in stellar evolution. Without supernova explosions and neutron star mergers, the universe would remain forever chemically primitive. The calcium in your bones was forged during explosive oxygen burning in massive stars. The iron in your blood was created during silicon burning in stellar cores or through explosive nucleosynthesis during supernova explosions. The trace amounts of gold and other precious metals in your body were synthesized during rapid neutron capture in cosmic violence. When you use any electronic device, remember that its functionality depends entirely on precisely controlled arrangements of elements that could only be created through stellar death. The silicon semiconductors, copper conductors, and rare earth magnets all represent cosmic treasures distributed through galactic space by exploding stars. The chemical complexity surrounding you reflects billions of years of galactic evolution, during which countless stellar generations lived, died, and enriched the interstellar medium with nucleosynthesis products. You exist during a cosmic epoch when sufficient chemical diversity has accumulated to enable technological civilization. You are not separate from this cosmic nucleosynthesis. You are composed of it. Every atom in your body heavier than hydrogen and helium was processed through stellar cores and distributed through space by dying stars. You represent the universe becoming conscious of its own chemical evolution. In a universe where stellar death enables chemical birth, where the most violent events create conditions for complexity and consciousness, and where every heavy element represents a triumph over nuclear physics limitations, the emergence of beings capable of understanding nucleosynthesis represents an even more remarkable achievement. The story of heavy element creation ultimately reveals the universe as a vast chemical evolution experiment, gradually increasing complexity through stellar cycles that transform simple atomic nuclei into the diverse periodic table that makes chemistry, biology, and technology possible. As we continue exploring cosmic chemical evolution, supernovas remind us that destruction and creation represent complementary aspects of cosmic development. The same stellar explosions that end individual stellar lives create the chemical foundation for countless future generations of stars, planets, and potentially living systems. If this journey through cosmic nucleosynthesis has deepened your appreciation for the stellar origins of matter, subscribe and give this video a thumbs up. In my exploration of how neutron stars forge elements impossible to create on Earth, I examine the exotic nuclear processes operating under conditions where matter approaches fundamental density limits. I'm certain it will expand your understanding of cosmic element creation. The next time you encounter any material object, remember that its heavy element content represents the accumulated nucleosynthesis from stellar generations spanning billions of years. Every manufactured product embodies cosmic history preserved in atomic nuclei forged during stellar death. The ultimate lesson of supernova nucleosynthesis is that we live in a universe where cosmic violence enables cosmic creativity, where stellar death births chemical complexity, and where the most extreme physics creates conditions for the emergence of consciousness capable of comprehending the nuclear processes that created its own material foundation. The elements heavier than iron exist as monuments to stellar sacrifice, dying stars that transform their nuclear fuel into the chemical diversity that makes rocky planets, complex molecules, and technological civilization possible. In studying these processes, we discover not just nuclear physics, but the cosmic connections that link stellar death to planetary birth, chemical evolution to biological evolution, and stellar violence to the emergence of consciousness. The heavy elements surrounding you carry stories of cosmic drama spanning galactic evolution, stellar lives measured in millions to billions of years, and explosive deaths occurring over seconds that forge atomic nuclei destined to persist for billions of years. In contemplating supernova nucleosynthesis, you participate in the universe's ongoing effort to understand how stellar death creates the material foundation for life, consciousness, and the scientific inquiry that reveals these cosmic connections.